Hi everybody, we are starting a new chapter, new modules, module 3, and we'll begin with the lesson 3.1 titled What Are the Chances? Let's go ahead and read the objectives so students will understand that a probability is a likelihood of an event occurring. There are different types of probability. Students will be able to determine a theoretical probability and compare theoretical probability to experimental probability. So the term probability you might have heard, I'm sure, before. So probability means a chance of something happening, and today we will define it clearly and sort of begin our chapter with the clear understanding of what the probability means. So let's begin with the classical example of a coin toss. It says in many situations, a decision is made based on the result of a coin toss, such as deciding field position in an NFL game or leaving a major decision up to fate. In general, we assume the coin is fair, meaning that it is not weighted, nor has two head sides. So it's either heads or tails. A classic question, if you flip a coin once, what is the probability it lands on heads? Write the result as both a fraction and a percent. I'll give you a moment. Okay, let's review. Of course, you know there are two equal chances for success. So probability it lands on heads is 1 out of 2, which is 0.5, which is the same thing as 50%. All right, so it's 50% heads and 50% tails. All right, now what do you think should happen if you were to flip a coin 1,000 times? How many times do you think it would head on heads? Why? I'll give you a moment. Well, if you flip it 1,000 times, you expect that 50% of all the tosses will result in heads, correct? Or lands on heads, or 50% of 1,000 will end up being on heads, and the other half will end on tails, which is 500. Does it necessarily mean you're going to get exactly 500? No, not necessarily. It can be a little more, it can be a little less, but our expectation it will be 500, correct? Well, keeping that in mind, there's an experiment that you can go ahead and try out. So what I would like for you to do, set a timer on your phone for 5 minutes, grab a coin, and go ahead and flip a coin for 5 minutes. Okay, and then record number of heads you got and a number of tails. So as you do this, you just simply do a tally. So, you have a heads and you have the tail. So you got a heads, put the, tally here, and keep going. Every time you get to 5, do the regular tally and then count. And once you do so, you will get numbers and put those numbers in the table. And I'll do the same thing. All right, so I got 20 heads and I got 26 tails. All right, so let's go ahead and for your numbers, go ahead and calculate the fraction of heads you got to the total number of flips. Okay, so I got 20 heads over the total number of flips. I add those together is 46. Let me go ahead and divide it and get the percent out of it. So 20 divided by 46 gives me about 43.5%. Okay, so I didn't quite get 50, but as we have an experiment, anything can happen. But as you can see, that percent is slightly less than 50, but it's still, high enough. All right, so let's keep going. Is your fraction in question 3 the same as your answer to question 1? No. I mean, why or why not? Well, it just depends on each experiment, because this is something that is still left to a chance. Okay, there's nothing that make this coin that I was just flipping to be that it has to give me exactly 50%. It doesn't need to, because any experiment can fluctuate a little higher, a little lower. So we do have, the experiment is still subject to chance. So what we're going to do next, we're going to try to take the results and we're going to try to build an understanding of a probability in a more general sense using that experiment. So now, again, since we're not working in groups and we can't go ahead and get the data from each other, so instead I'm going to display you the I'll display you the data from my other class that I collected. All right, so I have the data from 10 students. All right, and what I have right here is the total number of tosses, and I also just focusing on the number of heads obtained from those tosses. Okay, so what we're going to go ahead now is we're going to just calculate the percent of heads for each person that did that experiment. Okay, so we're going to go here and we'll divide the number of heads divided by the number of tosses. So we're going to divide it. So let me do that. So here I'm simply taking the column B and I'm dividing by the column A. I obtain. Alrighty, so I'm going to use Excel and I'll just scroll this down this way. So that gives me percent of heads. Well, it's written as a decimal. If I am going to go here and I'll change this to a percent, then I kind of neatly change this to a percent for me. Okay, I can make this a little bit more precise. So let's go ahead and maybe make the decimal point a little bit. Does it allow me? One moment. Here we go. So I moved it a little bit. So as you can see, it fluctuates. For some students, it was less than 50%. For some, it was a little higher than 50%. So then what we're going to do is something that's called a law of large numbers. We're going to go and we're going to compound all of these percentages together. So here's what I'm going to do. Check this out. So for the first one, for the first computation, I'm going to leave things the way they are. So I'm just going to take the number of heads and I'll divide this by the number of tosses. That's fine. Okay, so I get the same answer. I'll convert that into percent later. The next thing that I'm going to do, I'm going to compound them. So check this out. I'm going to take the sum. So I'm going to take the sum of these two. I guess, yeah, I'm just not using a keyboard. Here we go. So you see what I typed up? I basically doing the sum of the first two experiments. So the number of heads obtained by first two students, which is 45, and I divide by the total number of tosses both of them they did together. And then I click equal. All right, one moment. Here we go. So I got about 46%. And I'm going to keep going. But in order for me, for this to happen, what I'm going to do, I'm going to take the next one and I'm take the sum of these and I'm going to divide it by the sum of that. And then I press enter. You see what I'm doing? Check this out again. So for this one, I'm taking those three students, I'm adding the total number of heads, 3 of them got together, and I divided by the total number of tosses 3 of them got. You see what I'm doing? Summing up the first 3 students and then divided by the next 3. So what I want you to do, if you understand what I'm doing, I want you to calculate the cumulative percent of heads for the first 4 students. So I want you to add the 4 student heads together and divide it by the total number of tosses those 4 students got and get the percentage. All right? So I'll give you a moment. Just use a calculator. Divide these 4 numbers, add them up by the sum of these 4. And then I'll use Excel to confirm. Okay, so let's check. So if I scroll this down this way, I'm going to go ahead and I'm just going to increase it that way. And then it gives me 47.1 or 47.2%. And I'm going to keep going and let's see what we get. Alrighty, so check this out. So for example, for this one right here, for number, well, it's the student number 8. You take the sum of these divided by the sum of all the tosses and you keep going. Alright, so you keep going. Let me go ahead and change this into percent. Alright, and let's maybe have a little more decimal places so you could see it. And notice what's going on. So each of these students, for some of them it was as high as 54% and as low as 43%, like in my case. But once you start accumulating them, then there's something, notice, that's happening. You see these numbers? All right, once you accumulate them, so they no longer fluctuate as much, right? And you're actually getting an answer that is pretty close to what? So what do you see happening as you're moving down? What are these numbers sort of getting close to? All right, yes, they are getting close to 50%. It's getting closer to that 50% that we expected to see. And that's the idea of what we call the law of large numbers. So if you go back to the lesson, it says, what do you notice about the percent of heads as the total number of flip increases? We say that the percent cumulative percent of heads approaches 50%. Okay, it's getting closer and closer to that. So what we just did, it has a name. It's called the empirical probability. And empirical probability is coming from the experiment. I believe in our lesson they use the term the experimental probability. Experimental probability and empirical probability is basically when you take an experiment and you do it for a long period of time, and then you calculate the cumulative percentage of some kind of event, and that cumulative percentage is called the empirical probability. All right, now we're going to shift our attention from an experimental probability to something that called theoretical probability. All right, and we'll define the theoretical probability at the end. So problem situation number 2, how many boys? It is known that when a woman gives birth to a child, the child has a 50-50 chance of being a boy. Suppose that Janine wants to have 3 children. If she does have 3 children, one possibility is that she ends up having 3 boys. Another possibility is that she ends up having 2 boys and 1 girl. So first, an open-ended question, which I would like to for you to respond. Are these 2 outcomes equally likely? In other words, having 3 boys versus having 2 boys and 1 girl. What do you think? Is one more likely than the other? Let me give you a moment to respond. All right, so there's no right or wrong answer just yet, okay, because we don't really know what are the chances associated with each event. You might say that, well, having 3 boys is less likely because perhaps having 2 boys and a girl can be biologically it's more likely to happen because there are more chances for that. Perhaps you said that. Or you might have said, well, it's the same because it's just 3 children, so whatever happens, it's the same chance. Again, I'm not disclosing the answers just yet, as we will be able to develop this in this lesson, okay? Alrighty, another open-ended question here. What is the probability that all 3 children turn out to be boys? Can we actually come up with the number for the probability for that chance? It can be a fraction, a decimal, a percent. What do you think? Let me give you a moment. All right, again, we're not disclosing this, so we don't know yet what it's like. So what's the probability? Maybe you put 50%, maybe you put 25%, maybe you put something else. Again, I'll be able to see your responses, but it's perfectly fine if we're not sure, right? Because, it's really not clear what's happening. So right now, we'll try to be a little bit more systematic to try to get actual numbers. So it says one way to figure out probability is to consider all possible outcomes. In the case of a woman with 3 children, one possible outcome that her child is a girl and the other 2 are boys. Another possible outcome is that the first 2 children are boys and the third kid is a girl. This would be considered different outcomes. All right, so let's just maybe kind of abbreviate this. It says the first case that her first child is a girl and the other 2 are boys. So that's one outcome. And it says the other outcome is that the first two children are boys and the third one is a girl. And here it says that these outcomes is not the same. Even though there are two boys and one girl, the ages here are not the same, right? So for example, if the girl comes first, then she will be the oldest, correct? But if the girl comes last, then the girl would be the youngest. You see what I'm saying? So as an event, even though it's two boys, one girl, the outcome is different. It's a different possibility, and that is, the order of ages. Okay, so now question number 3. How many outcomes are possible that result in one girl and two boys? So far we have written 2 such outcomes. Is that it, or there can be more? All right, so what's the total number of the outcomes like that? Is it 1, 2, 3, 4, 5? How many? I'll give you a moment to respond. All right, well, if you understand that these 2 are different outcomes because they're different ages, then you probably figured out that the other outcome that has 2 boys and 1 girl is where the girl is a middle child. All right, so it's not the oldest, not the youngest, it's right in the middle. And that would be the third and the last possible outcome that happens. So the answer would be 3 possible outcomes. All right, so how about question 4? How many outcomes are possible that result in 3 boys? All right, I'll give you a moment. Well, when it comes to 3 boys, there's only one, there's one possible outcome, because it's 3 boys, so they can be of different ages, but whatever their age is, that would be the outcome, right? It's boy followed by a boy followed by a boy, so there's only one. There's no way you can rearrange it to make it different. You see it? All right, so now if you're looking at these 2, how now compare the likelihood of having 3 boys to having 2 boys and a girl? Write your answer in a complete sentence using precise mathematical language. So going back to when we use comparison in chapter 1, if we say how likely, all right, how can you compare it? What word can you use? Let me give you a chance to say it. All right, well, if the number of outcomes for 2 boys and 1 girl is 3, while for the 3 boys such outcome is only 1, then you might say that the likelihood or the probability of having 2 boys and 1 girl is 3 times as likely as having 3 boys. Because, 1 is 3, the other one is only 1, so it's 3 times as likely. All right, so when it comes to siblings, seeing 2 boys and 1 girl is 3 times as likely as seeing just boys as siblings. All right, now let's go ahead and try to make it even more mathematical. So question 6, if the middle child is a girl and the other 2 children are boys, this outcome could be written as BGB, which already did it before. Write all possible outcomes when having 3 kids. So far, we have seen BBB, and then we got GBB, BBG, BGB. So far we got 4. Can we write all the possible outcomes of any combination of biological genders that you can list? So can you list them all? I'll give you a moment. Alrighty, so how many did you get? Well, altogether, there's actually 8 possible outcomes that you can get. So let's go ahead and list them all, okay? A couple of ways to do this, all right? A couple of ways to do it. I want to show you several, okay? So one way is to write down just a permutation of all the possibilities. For instance, look, if you look at 2 kids, boy, 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 girl, girl, boy, and then girl, girl, So there's a 4 possibilities of having 2 children, 2 siblings, right? So it's either 2 boys, 2 girls, or boy, girl, but different ages. So there are 4 different possibilities, right? So that's for 2 kids. And let's say the 3rd kid comes in, into the picture, right? So the 3rd one. So if it's a 3rd one, let's say it's the youngest one. Let's say that kid is a boy. All right, so you have already 2 siblings, and now you have the 3rd one, which happened to be a boy. That gives you, 4 different outcomes. But then you could have the same outcome from before, which is having, 4 different possibilities. And now a girl comes into the picture, right? So you got another girl right here, and that creates another 4. So if you count, there are total 8 different outcomes. All right, so that's one way you could have done it. The other way you could have done it is like this. You could say, okay, we got the first kid as a boy, right? Then, so a boy, then you got boy and a girl as the second sibling. Then the 3rd possibility could be that if that's a boy, it could have followed by a boy and a girl. And if it's a girl, it could have followed by the boy and a girl. All right, so that gives you 4, right? So if you look at this, you can see, okay, this is 1. All right, then you have the other. Then you got the 3rd. All of these are different. And then you got the 4th. See, like that? So that's if you start with the boy. Now, if you start with the girl, you get the same possibility. You got boy or girl. Here you can have boy or girl. And here you got boy or girl. So you got another 4. So 1, 2, 3, 4, 5, 6, 7, 8. That's also matches what we got. All right. So all of these are different outcomes. There are 8 outcomes. 8 different outcomes. So here we go. It's 8 different outcomes. All of them are different. You can check them out. We already discussed that, for example, boy, boy, girl, and girl, boy, boy is not the same outcome because the ages are different. But the, altogether we got 8. So question 7, what is the probability that Janine's 3 children will be the same biological gender? So, looking at this, I think it's time for us to define something that's called classical probability. And a classical probability is defined as well, let me write it. Classical probability is defined as a fraction where the denominator is the total number of outcomes for an event. All right, and the numerator is the number of ways outcome can occur. So in other words, if we want to find what's the probability that there are 3 children will be of the same gender, well, what are the total number of outcomes we got? There are 8 outcomes. And now we need the total number of ways an outcome can occur, the one that we measure the probability of. It says, what is the probability that the children has the same gender? Well, same gender means all boys or all girls, correct? So there are only 2 such possibility out of 8, which is the total. So if you simplify, it's going to be a quarter, which is 25%. The probability can be written as a fraction, decimal, and percent. There is no, depends. It really depends on the question. So you could be asked to write the probability either way. So there's a 25% chance that they all going to be of the same gender. 1 out of 4 chances. And now finally we can kind of calculate the probability that we were asked before. So if she has 2 kids, well, actually, no. This question is just asking us if she has 2 kids who are boys, what is the probability that the third one is also a boy? So if we already know that she had 2 boys, what would be probability that it's a boy again? Let me give you a moment. Well, this one is actually not a classical probability. Well, it is a classical probability question, but it's a little tricky. So we're not counting what's the probability of her having 3 boys, because that would be 1 out of 8. The question is, how likely is she going to have a boy, given that she already had 2 boys? But because each child is a separate outcome, there's a 50-50% for each. So it doesn't matter, what has happened before. The probability that the third one will be a boy, or actually any other child will be of whatever gender, is still 50-50. So here, it's not, it's not going to change. Now, one thing I do want to come back to, though, is to look at these 3. Remember that question? Oh, actually, hold on. This question right here. And we can kind of answer them now. It says, if she does have 3 children, one possibility is that she ends up having 3 boys. Another possibility, she ends up having 2 boys and 1 girl. Are these possibilities equally likely? Well, having 3 boys is this, correct? And the probability of that, probability of having 3 boys, there's 1 out of 8 chances, right? Because there were 8 chances that we wrote down. Boy, boy, boy was only 1, so it's 1 out of 8. But probability that she ends up having 2 boys and 1 girl, here it's this, it's this, or it's that, right? The order matters. These are 3 different outcomes depending on the age of a girl. Is it the youngest, the older, is it the middle sister? So there are 3. So the probability of that is 3 out of 8. Now, if you look at these 2 fractions together, this 3/8 is higher than 1/8. So they're not equally likely. And not only that, this number is 3 times as likely as the other. All right, what's the probability that all 3 children turn out to be boys? We already said it. It's 1 out of 8. So now look, this idea of counting the cases and then writing the probability associated with that is called a classical probability. You can also see a classical probability when you throw a coin, right? That's one example. Biological gender is the other. Some other examples are throwing a die that has 6 faces, and each face is equally likely. So for example, probability that you get, let's say, a 2, well, there's 1 such outcome out of 6 possibilities. So probability here is 1 out of 6. Probability that you get an even number when you throw a die is going to be, there are, what are the even numbers on the die? It's 2, 4, and 6. So there are 3 possible outcomes out of 6, which is 3 out of 6, which equals to 1/2. So on. So when it comes to classical probability, we need to be able to identify what are our outcomes and how many chances do we have for success happening, and we write it as a probability. Okay, let's see if we maybe have another example of this.